Okay. So we are studying radiation field of an antenna. Okay. So we have started our study with what is called magnetic vector potential. Okay. So we have found the magnetic vector potential. Okay. So this is Z, Y, and this is X. Okay. So I use Cartesian coordinate. Okay. Rectangular coordinate. Okay. So if you have a current distribution here, okay, current distribution here. So this is a position. Okay. So you can see that that position has a magnitude and also it has a direction. Okay. So it is a vector. Okay. So we have denoted this position vector using R dash. Okay. So this R dash bar is a position vector of the current distribution. Okay. And we have found the magnetic vector potential. Okay. Magnetic vector potential at any position. Okay. At any position in the space. Okay. So that position vector is we denoted as R bar. Okay. So we have learned these things. Okay. Bar. Okay. And we try to get the solution. Okay. Solution. It is for actually uh, unbounded free space. Okay. This is the solution for, this is actually a bar solution for unbounded free space, and it is in phasor domain. Okay, that means no time. The time should be there. Okay, time and the both time and the position should be there, but we get it in phasor domain, so the time variable is not included with this expression. Okay, because we get it in phasor domain. Okay, our solution is in phasor domain for unbounded free space. Okay, and so we are going to find the magnetic vector potential here due to this current distribution J. Okay, and this is we denoted as R. This position with respect to this point we denoted as R. Okay, so with respect to the with respect to here at the 0, okay, that will be the magnitude will be R minus R dash, the magnitude. Okay, so this is the magnitude of R. Okay, and the position we define as N. Okay, N hat. Okay, so this is the unit vector. Okay, this is a unit vector. Okay, so that is this direction. Okay, with respect to this one, with respect to this position. Okay, so we define this direction. Okay, so along this direction the unit vector is N hat. We define it like this. Okay, and we have found the solution for unbounded free space in phasor domain. Okay, so it is a function of R. Okay, function of the position R. Okay, actually the R, it should be R bar, position vector. Okay, and we get naught divided by 4, 5. Okay, and we have to do the volume integral. Okay, and this J R dash So this is the current distribution at this point. Okay, this is the current distribution at this point. Okay, JR dash bar. Okay, e to the power minus JKR divided by R in with respect to dr bar. Okay, so this is the solution. Okay, this is the solution. I think we have found this one previously. Okay, and next we have done an assumption. Okay, we have done a assumption that is for far field. Okay, so that is called far field approximation. Okay, so we have done the far field approximation. Okay, so I write it here. Okay, so we have done the far field approximation. Far field approximation. Okay, so what is that? The far field approximation means this point, the position we consider the magnetic vector potential, that location is very far away from this point. Okay, from this point, from the current distribution, our magnetic vector potential location is very far away from this location. Okay, so that is the far field approximation. Okay, so because this point, this is the point we consider this magnetic vector potential solution in phasor domain. Okay, now that position is very far away from this current distribution. Okay, so due to this far field approximation, okay, we can assume that, so I will write it here, is that y x. Okay, so this is the current distribution J. Okay, and now position is very far away. Okay, so this is the position vector for that location. Okay, that is R bar. Let's say that the vector, unit vector along this direction from initial to this position, that is R hat. Okay, so this is the unit vector. Okay, it indicates the direction actually. Okay, so this unit vector indicate the direction. Okay, so this is a position vector. Okay, so this has a magnitude and direction. This has the magnitude is unity. Okay, magnitude is unity, and it actually it indicate the direction. No, indicate a direction. Okay, so that direction is our hat. Okay, and we assume that due to this point and this point is very far away, so this is R dash bar. Okay, this one and this one parallel. Okay, so it is like this. Okay, I can't write it clearly. Okay, so it means that this line and this line parallel. Okay, what is this line? That is R. Okay, so what is the direction we have defined? That is n hat. This is the unit vector in this direction. So that is n hat. Okay, so what this means, this position and these positions are, this line and this line is parallel. So R hat and n hat is in same direction. So they are equal. Okay, so that is the far field approximation. R hat completely equal to n hat. Okay, so this is the far field approximation. Okay, far field approximation, and also we have consider a line current here. Okay, so this is a line, any line. Okay, the current is flowing through this line, and we consider a point. Okay, we consider a point of this conductor. Okay, and we have adopted our solution, that is for unbounded free space. Okay, at far field, due to line current. Okay, then your magnetic vector potential, okay, then your magnetic vector potential will be approximately equal to, because we are doing some assumption here, okay, mu naught e to the power minus jkr and 45r. Okay, so your integration should be done. So this is a line current. Okay, so actually this is a volume, this j is a volume. Okay, so that is why you have to do a volume integral. Okay, but this is a line current. Okay, so that volume integral will become a line integral. Okay, so you have evaluate the line integral along this conductor. Okay, you have to do the integral along this conductor. Okay, that carry the current. Okay, and you have I R dash. Okay, so this is the current distribution at this point. Okay, this is the current distribution e to the power jk in hat R dash dl dash. Okay, so this is the solution at the far field due to a line current in unbounded free space in phasor domain. Okay, so this is the solution for that magnetic vector potential. Okay, so there are many conditions here. This is for unbounded free space. Okay, at far field. Okay, for a line current in phasor domain. Okay, so this is the solution for magnetic vector potential. Okay, and once you have found, okay, so this line current, this is the current, so you can consider this line as this current conductor as the antenna. Okay, so once you have once you have found this magnetic vector potential, you can calculate the magnetic field, that is approximately equal to minus jk divided by mu naught n hat cross product A. Okay, so you have to do the cross product with this one and the magnetic vector potential. Okay, so this is the magnetic field. Okay, so this is the magnetic field. Okay, and then once you have found the magnetic field, you can find the electric field also using this identity in hat which. Okay, so this is the magnetic vector, magnetic field. Okay, and if you multiply it by neta in hat cross product, okay, if you get the cross product, you can get the E field also. Okay, and this one, this derivation and this derivation we didn't done. Okay, we haven't done these derivations. Okay, but if you need, actually these derivations are in our reference book also. Okay, so if you want to study it, you can refer the reference book. Okay, so there are many assumptions and as well as some approximations. Okay. So, however, we can find these kind of identities for magnetic field and E field. Okay. So, first we have to find the magnetic vector potential. Okay. So, so this K is called wave number, and it is defined as 2 pi by lambda. Okay. And this is the wave impedance. Okay. This is called, this neta is called wave impedance, and it is also constant. Okay. Wave impedance. Okay. But this wave number is not a constant, it is depending on the frequency. Okay. That the antenna is radiating. Okay. So that is it. Okay. So we in previous week we tried to use this identity to find the radiation field of a infinitesimal dipole. Okay. Infinitesimal dipole. It is so my pronunciation may be not correct. Okay. It is pronounced in an infinitesimal dipole or something. I can't remember it. Okay. Anyway, I have used to pronounce it as infinitesimal dipole. Maybe my pronunciation is not 100% correctly. Okay. Please check the Google for the correct pronunciation. Okay. So infinitesimal. It is, as I can remember, it is pronounced as infinitesimal dipole. Okay. Infinitesimal dipole. Okay. I'm not sure. Please check. Okay. So anyway, I'm used to pronounce it as infinitesimal dipole. So maybe when I'm doing this, I will pronounce it that like this. Okay. Don't take it seriously. Okay. So what is infinitesimal dipole means? The dipole length is very much less than the wavelength. Okay. So that is the infinitesimal dipole. Okay. And if you consider current, if you consider the current distribution, okay, if you consider the current distribution, okay, that is uniform. This current distribution is uniform. Okay, it is not changing because the length is very small. Because this length is very small, we can assume that the current distribution is uniform. Okay, so I think we have tried to find the magnetic vector potential of a dipole antenna. Okay, it is not much difficult. Okay, so we consider the rectangular coordinate system. Okay, so this is Z, X, Y. Okay, and we have placed our dipole along this Z axis. Okay, so we have considered, we have put our dipole along this Z axis. The feed point is this one. Okay, so this is the feed point, the initial point. Okay, 0. Okay, so this is our dipole. Okay, so we place it symmetrically. Okay, in this y-axis, based on this y-axis. So the total length is L. Okay, so you can consider this length as L by 2 and also this length as L by 2. Okay, so this Z position is plus L by 2 and this Z position will be minus L by 2. Okay, so this is minus L by 2 to plus L by 2. So the total length is L. Okay. Okay. And so So now this is your current distribution. Okay. Now, so this is the line. Okay. So this is the line. Now this is the line. Okay. That is the current carrying conductor. Okay. This one. Okay. So this one. Now this one is just a simple line. Okay. Along the Z axis. Okay. So you can get any position. You can consider any position. Okay. So here also you have consider a general point, no? General point. Okay. So that general point you have defined as R, the position vector. Okay. The position you have defined as R bar dash. Okay. So now that position, that R bar dash, this position is in Z axis, no? This is in Z axis, no? Okay. So that is the Z position, no? Okay. So let's denote that position as Z dash. Okay. Z dash. Okay. So I think it is clear because you have, so previously we have considered a general line. Okay. And we have considered a position that is R dash bar. Okay. So that is our position. Now we have placed that line along the Z axis. Okay. So our position should be in Z axis, no? So let's denote it as Z dash. Okay. So you can consider this as Z dash. Okay. Okay. Now, so the current distribution IR dash is uniform. That means the current is not changed along this line. Okay. So let's say that current is I. Okay. Current is I. And you know that current has a direction. No, current is a direction. Current has a direction. Okay. So what is the direction of the current? Let's say that it is in Z direction. No, because it is, we have placed this antenna, this current, this conductor on the Z axis. So the current direction should be the direction of Z axis. No, so the direction we defined, we denoted using a unit vector, that is Z hat. Okay. So the current is I Z hat. So this is the magnitude and this is the vector part. Okay. So this is the current through this conductor. So that is uniform, not changed. Okay. So actually that is the current at this point R dash. Okay. So it is nothing but I Z hat. Okay. I think you can understand this because this current is in Z direction. Okay. Okay. And what are the other things we should consider? Okay, so in the same, so now you are going to find the far field radiation. Okay, so you have to consider a far away point like this. Okay, and that point from here, it is referred as R. No, so this position vector is we previously defined as R bar. Okay. This one. Okay, so it is defined by R bar. Okay, so here also that position we defined as R bar. Okay, so now you are going to find the magnetic vector potential here. Okay. 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 So so we have this identity. Okay, we have this identity. Now we have to write this identity for this situation. No, we have to write this. We have to change this identity with respect to this situation. No, okay. So if I right A, okay, is approximately equal to, these are same, mu naught e to the power minus jkr divided by 4 5 r, okay. So that is not changing because that position we have considered as r, okay. So it is r, okay, because it is the position vector we have defined it as r bar, okay. So this is the, actually this r is the uh, distance from here to here, okay. So this is the distance from here to here. Actually the r bar is nothing but r into r hat, okay. The r hat is the unit vector in this direction, okay. So this is r is the magnitude, and the magnitude is multiplied by the unit vector, you get the complete vector, that is r bar, okay. So I think now you can understand these things, okay. These are simple vector things, okay. So here we have considered the distance from the initial, okay. So that is not changing, okay. And you have to do the integral you have to do along the line, okay. So what is the integral you have to do here along this line, no? Okay. So you have to, this is the lower limit for this line and this is the upper limit for this line, okay. So what is the lower limit? That is minus L by 2 and this is plus L by 2, okay. So these are the what is this called? These are the limits, the lower limits and upper limits for the integral, okay. And then you have the current distribution IR dash, okay. You have the current distribution IR dash, okay. This one IR dash, okay. So what is IR dash here? So that is the I is uniform and it is in Z direction, I Z, okay. So in this case, this is the current, okay. And e to the power jk n hat, okay. The n hat is the in far field n hat, okay. For far field n hat is completely equal to r hat, okay. This is the far field approximation, okay. But anyway here we put that as n hat dot, that should be r dash, no, r dash, that means this position vector, okay. This position vector, what is that one? That is actually the z hat, no. That is actually nothing but uh, z bar, okay. Z bar, okay. So this z bar is the z bar is the magnitude, okay. And so z bar, this is the magnetic. If you put this bar, okay, the underline, okay. So this represent a vector, okay. And now I have here, I have marked the I have marked not the vector, just the position, okay. But that is the vector, no? That is a vector and it has a magnitude. The magnitude is z bar. And what is the direction? Direction is z hat, no? This z dash vector direction is z hat because it is in z direction, okay. It is in z axis, okay. So this vector is equal to z dash into z hat, okay. Z dash into z hat, okay. So here actually you have to put the, here you have to put the vector, okay. This is the vector, I'm sorry, the underscore should be here, okay. So this is the vector, you have to put the r bar dash, okay. So what is the r bar dash? Okay, okay, r bar dash. Now it is actually z bar dash, okay. Now in our case, r bar dash is completely equal to z bar dash, and z bar dash is equal to the magnitude and the unit vector, magnitude into unit vector. So this is the complete vector. Okay. So it is z dash z bar. Okay. So this is nothing but, okay. So this is nothing but r dash bar. Okay. So this is a vector. Okay. These are not vectors. These are just distance. Okay. From here to here. Distance. The bar is not here. Okay. But this is, here you have to put the bar. This is a vector. Okay. Okay. Now you have to do, okay, dl dash. Okay. Now dl, l means, okay, along this line, no? Okay, that is dl, along this line. Now that line is along the z-axis. That line is along the z-axis. So dl dash, this is l dash, now is in z-axis. Okay, so it should be dz. No, it should be definitely dz. Okay, so I have put this as z dash. Okay, so here also I have put it like z dash, dz dash. Okay, so this dl dash will become dz dash. Okay, so this is the solution. This is the solution, or this is the uh, expression for a magnitude. This is the expression for the magnetic vector potential, due to this infinitely small dipole. Okay. So now, if you consider this one, n hat z hat. So what is the value of this? N hat z hat. Okay. So actually this r, okay, we define this r. Okay, so this is the r, no? So if you define this r using spherical coordinate, okay, so this r location will be r theta phi. Okay, so this is the r location. If you consider this r bar in spherical coordinate, so it is r theta phi. Okay, so so you know that this is the, so if you consider is spherical coordinate, okay, so this is the r hat direction, no? This r hat direction. Okay, so now you have to find n hat dot z hat. So you have to get the dot product. You have to get the dot product. Okay, so what you have to get? Okay, dot product, no? So you have to get n hat, the magnitude of n hat, the magnitude of z hat, cos theta. The theta, let's say that cos alpha. So that is the angle between these two vectors. Okay, so if this is n hat and if this is z hat and the angle is alpha, so this is the definition for dot product. You already know this. We have discussed these things. Okay, so this is dot product. Okay, so now you have to take the dot product. Okay, so now consider this r is in spherical coordinate, so the vector is, the position is r hat. Okay, and the angle from z axis to this position in spherical coordinate, that is the theta, no? That is theta. Okay, so if I ask you to find the z hat dot r hat, okay, so you can easily find them. Okay, so z hat is in this direction. Okay, and you know that r hat is in this direction. Okay, and the theta is the angle between these two line, z hat and r hat. Okay, and z theta direction is in this direction actually. Okay, So this is the R direction, and this is the theta direction. Let's say that it is theta hat. Okay. And you know that if this is X, okay, if this is X, okay, and this will be 5. Okay. So this is 5 direction. This is 5 direction. Okay. This is 5 hat. Okay. So it is in this direction. Okay. Okay. Inside the paper. Okay. So you can use, so we have learned that we can use right hand tool to get the direction of these vectors. Okay. So you have to find the z hat dot r hat. Okay. So what is the answer? Z hat magnitude. So that is 1 because this is a unit vector. And r hat magnitude is 1. That is a unit vector. And you have cos theta here. Okay. So this is the answer for z hat dot r hat. Okay. So, but now you have to find the answer. You have to find this one, no? N hat dot z hat. So you need to find this one. Okay. But you can easily find this one, no? Using the rectangular coordinate and spherical coordinate, you can easily find this one. But anyway, you need to find this one. Okay. So how you find this one using this one? Can you see any relationship between this one and this one? Okay. So try to find it, try to figure out it. What is the relationship? Okay. So pause the video and try to understand it by yourself. Anyway, you already know that what is the relationship. Okay. So this point is in far field. This point is in far field. Okay. So r hat is completely equal to z hat. Sorry, n hat. No? At the far field, r hat is complete equal to n hat. N hat. So n hat is this direction. Okay, from here to this point, from antenna to the considered point. So that direction is n hat. Okay, and this direction is r hat. Okay, at the far field. Okay, at the far field, this one and this one considered as parallel. Okay, so r hat is completely equal to n hat. Okay, so r hat is completely equal to by n hat. Okay, so n hat dot z hat is nothing but r hat dot z hat. So what is that? That is equal to cos theta. This is the answer. Okay, so you have to, so you can see that here you have to get the dot product, no? N hat is z hat. Okay, so n hat is z hat you can write as cos theta. Okay, so your magnetic vector potential will become mu naught e to the power minus jkr. Okay, and equal 5r. Okay, minus L by 2 to plus L by 2 z hat I e to the power jk z dash cos theta. Okay, because n hat and z hat you have found that it is cos theta. Okay, and it is in z dash. Okay, so actually you can consider this z hat as z and dz dash as dz. No issue. Okay, z and dz you can consider, no issue. Okay, I think that may be yeah, that is correct. Okay, so this is a general. So here I have get the general point in the z axis as z dash. Okay, you can get as z. Okay, no issue. So it will be z dz. Okay, Now you have to do this integration. Okay. So before this integration, you are doing assumption again. Okay. So this Z dash is the value on this conductor, no? Is the value of this infinite small dipole. Okay. So this Z dash, the upper limit is minus L by 2. Sorry, lower limit is minus L by 2. Upper limit is plus L by 2. So it is very, very small value. Okay, it is very small value. So you can consider, okay, because L is very much less than lambda, you can consider this Z dash is limiting to 0. Okay, because this Z dash is also very small. It should be very small. So this L is very less means Z dash is limiting to 0. This is also an assumption. Okay, and because this limit into 0, you can consider this. Okay, so here is a dash, no? So this one is limiting to 0 means e to the power jk is a dash cos theta is limiting to 1, no? So is a dash is limiting to 0 means e to the power jk is a dash cos theta, because this is now 0. Okay, e to the power 0. So it is limiting to 1. Okay, so you can assume that this part is equal to 1. Okay, so your integration will be very easy. Okay, so now A is equal to mu naught e to the power minus jkr for 5r. Okay, minus L by 2 to plus L by 2. Okay, so is that hat I, those are also constant. Okay, so you can get them out. Okay, and here this is 1. Okay, so you have 1 here in Z dash. Okay, so what is the answer? The Z dash means it is Z dash. So L by 2 minus L by 2, you will get it. Okay, so you will get mu naught e to the power minus jkr I L is at hat divided by 4 5 r. Okay, so this is the magnetic vector potential at this point r distance. Okay, due to this current distribution, due to this infinitesimal lambda. Okay. Okay, so you can write it as, okay, A is equal to Z hat. So that is the direction of this magnetic vector potential. So this is a vector, okay, and you have direction. Okay, and you have mu naught I L divided by 4 5 r. Okay, e to the power minus jkr. Okay, so this is the magnetic vector potential at distance r due to the infinitesimal antenna. Okay, okay, so this is the far field magnetic vector potential due to a infinitesimal dipole. Okay, so this is far field magnetic vector potential due to infinite small dipole. Okay, so this is the solution for the magnetic vector potential. Okay, so we have found the magnetic vector potential. Now you can easily find the H field. Okay, the magnetic field. So magnetic field is nothing but minus jk divided by mu naught, no? Minus jk divided by mu naught n hat cross product A, n hat cross product A. Okay, now you have found this one. Okay, so you have to apply this value here. Okay, substitute this value here. Okay, then you can find the magnetic vector, magnetic field. Okay, so that is minus J mu JK mu naught n hat into this one. Okay, so this is also a vector. Okay, so you have to consider that one. Z hat mu naught I L 4 5 R e to the power minus 3k. Okay, so you can see that this is also a vector. Okay, the direction is n hat. This is also a vector. That is the magnetic vector potential. The direction is z hat. Okay, so the magnetic vector potential due to this current distribution, due to this finite small antenna, is in z direction, not this direction. Is in z direction, not in n direction. Okay, the n direction is here, so n is equal to r dash, no? Okay, so it is not in r hat direction, it is in z direction. The magnetic vector is in z direction, it's in z hat. Okay, so so this is the magnitude and this is the direction, and this is the magnitude and this is the direction. Okay, so you can ignore this direction and you can only consider these two vectors. Okay, so if you find the cross product, okay, if you find the cross product of n hat into z hat, okay, so you can find the total vector, no? Okay, so you can, so these are not changing, these are magnitude, that is not changing. Okay, that is not changing, these are same. Okay, so how to find this cross product? Okay, so you already know that the resultant should also be a vector. Okay, this is a cross product, not the dot product. So this product, the result of this dot product is also a vector. Okay, and what is the direction for this vector? That is perpendicular to both n hat and z hat. Okay, so if you want to find the cross product of these two, okay, so you have to find the n, you have to, you can find it by taking, you can find it by taking n hat magnitude, z hat magnitude, sine, okay, sine the angle between these two vector. Okay, and you will get another vector, no, it is also another vector. Okay, so there may be any unit vector. Okay, let's say that it is q. Okay, so q hat maybe. Okay, so now we have to find this one, we have to find this alpha and we have to find this direction. Okay, so we already know that n hat magnitude this one, z hat magnitude this one. Okay, so how to find this? Okay, so again you can consider the far field approximation. What is the far field approximation? N hat is completely equal to r hat. Now this r hat and z hat you already know. Okay, so if you consider this is z hat, okay, and this is y hat, and this is x hat. Okay, and if you consider r hat here, okay, r hat here, okay, so this is the theta, okay, the angle between these two vectors. Okay, and okay, now you have to find, okay, is at hat and r hat, no, is at hat and r hat. Okay, so the r hat is in this direction. Okay, r hat is this direction. So z hat is in this direction. No, z hat is in this direction. Okay, so this is the theta. Okay, so you have to get z hat r hat sine theta. That means this one, this vector. This is z hat sine theta. Okay, so you have to find the vector that perpendicular to both this r hat and this line. Okay, the z hat sine theta. So what is that? Okay, so that should be in this direction. No, that should be in this direction inside the paper. Okay, because this is at this direction and r hat is this direction. And if you find the vector inside or outside perpendicular to this plane, the r hat and z hat is in, let's say that it is in 2 dimension, it is in the paper. Okay, so the perpendicular direction for both this r hat and z hat is inside the paper or outside the paper. Okay, so that is the vector, that is the vector, that is the direction for r hat cross product is z hat. Okay, so what is that vector? That is nothing but phi hat. No, okay, so if you consider the phi, okay, so it is in this direction. So phi is inside the paper. Okay, it is perpendicular to r. Okay, so it is in like this. Okay, so this is phi hat. Okay, and theta hat, this is z hat. Okay, theta hat is in this direction. Theta hat is this direction. Phi hat is in this direction inside the paper. Okay, so this is theta hat. Okay, so the vector, resultant vector is phi hat or minus phi hat. Inside the paper, it will be phi hat. If it is outside the paper, it is z hat. Okay, so use the what is called the right hand rule, and you will get that is outside the paper. Okay, that is minus phi hat. Okay, so if you get, if you want to find this one, n hat cross product z hat, it will become r hat cross product z hat. So it is nothing 1 into 1 sine theta phi hat, but it is in minus direction outside the paper. Okay, so you will get sine minus sine theta phi hat. Okay, so I think you can get this one by yourself. Okay, to try to get this one by yourself using the right hand rule. Okay, so you can see that you will get the h. Okay, so this is the magnitude, it will not change in minus jk mu naught into, this is the magnitude, mu naught il e to the power minus jkr, so 5r. Okay, and n hat in n hat cross product is z hat, so that is minus sine theta 5 hat, minus sine theta 5 hat. Okay, so you can see that H field is in 5 hat direction. Okay, so due to this current, the H field is 5 hat direction. So that means it is inside the paper. This is the 5 hat. This is the direction for H field. Okay, and Z hat is the direction for magnetic vector potential. Okay, so we have found that one also. Okay, so you can see that mu naught will be cancelled out. Okay, and this minus and minus will become plus. So you will have jk il e to the power minus jkr sine theta divided by 4 5 r, that is in 5 hat direction. Okay, so this is the H field. Okay, now once you find the H field, you can find the E field also. Okay, so very easily you can find the E field. Okay, so E field is minus neta. Okay, now this is in free space, so neta is, we can denote neta naught. Okay, n hat into H. Okay, so if you apply this value for H, you can find the E also. So that is neta, okay, n hat into this one, okay, so it will be j k I l e to the power minus j k r sine theta 5 hat divided by 4 5 r. Okay, so you again you can see that this is a magnitude and this is also a magnitude, and these are the vectors. Okay, so now you have to find n hat and 5 hat. Okay, so n hat is nothing but r hat. Okay, so you have to find the r hat into 5 hat. Okay, so what is the answer? Okay, so r hat is, so if you consider this is x at yx. Okay, so if you consider this one will be the r hat, simple r hat. Okay, so your theta is in this direction now, so you are measuring theta in this direction, so this is the vector for theta. Okay, and 5 you are measuring this direction. Okay, then this is the, so inside. Okay, I can't write it. Okay, so that is inside the paper. Okay, and this is the 5 hat. Okay, now you are going to find r hat into 5 hat. So what is that one? Okay, so it is very easy. R hat into 5 hat is theta hat, no? Okay, so that is theta hat. So you know that z hat into y hat will be x hat. No, x hat into y hat should be z hat. Okay, in the same manner, r hat theta hat will be 5 hat. Okay, so you can use the right hand rule. Okay, so these are unit vectors. Okay, so the angle between two are sine 90. The angle is 90 because these are perpendicular. Sine 90 is 1. Okay, so you have theta hat. Okay, so okay, correct, no? Yeah, theta hat or hat dot 5 hat. Okay, so you can get E is equal to neta jk I l e to the power minus jk r sine theta divided by 4 5 r. Okay, 5 hat n hat, that means 5 hat r hat, that is nothing but theta hat. Okay, so this is the value for E field. Okay, so you can see that E field is in z direction, theta direction. Okay, so the E field is in theta direction. Okay, so you can see that the E field. Okay, so if you consider H field, okay, due to the infinitely small antenna, the H field is in 5 direction. Okay, that means inside the paper, this is the 5 direction, this is the magnetic field. Okay, and H is in the E field, in the electric field in theta hat. Okay, so theta hat is in this direction. This is a theta hat. Okay, so this is E field. Okay, so you can see that the magnetic field and the E field are perpendicular each other. No, perpendicular to each other. So you already know that. For electromagnetic wave, magnetic field and E field is perpendicular to each other. Okay, so we can get them. Okay, so this is how we find the H field and E field of an infinitely small antenna. Okay, so we have to start it with the magnetic vector potential, then you can find the H and E field. Okay, so once you find this H and E field, okay, so there are some other important parameter also related with the antenna. Okay, and you can find them. Okay, so we will see another very important parameter. Okay, that is called average power density. Okay, average power density of an antenna. Of an antenna. Okay, so what is average power density mean? It is power radiated through a cross section. Okay, so it is the power radiated through a unit cross section. Okay, power radiated through a unit cross section. So that is called average power density. Okay, and it is denoted using SAVG, the average power density. Okay, so average power density can be calculated as, okay, average power density can be calculated as um, like this. Uh, and you have to calculate, and you have to get the E field, and you have to get the magnitude of E field, and you have to square it, and it should be divided by n theta, n theta. Okay, and it is also equal to half. Okay, if you get the real part of E and H, you can get the cross product of E and H. As I can remember, this should be H conjugate. Okay, I can remember maybe. And if you get the real parts and if you divided it by half, you can again get the average power. Okay, so this is not a vector actually, this is a scalar. It is a power. The power doesn't have the energy doesn't have a direction. No, it should be a scalar. Okay, so so actually we are not going to use this identity. Okay, to find the average power density. Okay, you can use this identity easily because you already have found the E field. Okay, so what you have to get is the magnitude of the E field, and you have to square it and divided by half. Okay, and also it is divided by the wave impedance. You can get the power average. So it is very easy. Okay, so let's say, okay, okay, so this is the definition. Okay, this is the definition for the average power density. We are not going to derive these things. Okay, but we use this identity and calculate the S average for infinitely small dipole. So what is that? Okay, so you have already calculated the E field. Okay, so this is the E field. This is the E field. Okay, and you can see that this is the magnitude and this is the vector part. Okay, so if you remove the vector, okay, so this will be the magnitude only. Okay, so E magnitude is nothing but this one, njkil e to the power jkr sine theta 4 5 r. Okay, so that is the uh, okay. Energy is also should be a vector, no? The power, energy means uh, the the work done, no? Okay, so if you have put the force, okay, F, F into L is the energy, no? F into L is the energy. F is the force and it is multiplied by the length, you will get the energy. No? So F is a vector actually. So energy also should be a vector, no? I'm not clear it. I can't remember it. I will check. Okay. Mm, this also should be a vector. If this, if we see, if we have seen in this way, okay. So give me a moment to check it. Yeah. So I think this also should be a vector, no? Because this should also should be a vector because you already know that if we get if you have a mass, okay, and if you are using F force to move this, and if you move it the L distance, okay, total, so the total work done, work done, okay, is equal to F into L, okay. So this is the energy, no, that is measured by Joule, okay. So F is a vector and L is not a vector, it is a scalar. Distribution. Yeah, L also can be considered as a vector, no? Um, so anyway, the work should be a vector, okay? Work should be a vector, okay? So the power also should be a vector, okay? So if you consider antenna here, okay, due to R distance, okay, so the power is radiating like this, okay? So maybe power is radiating, okay? And you get a unit cross section with this sphere, okay? If you get a unit cross section with this sphere, okay, and power dissipated through this unit vector is is the average power density. So that is the definition of the average power density, okay. So it should be perpendicular to this cross section. That power dissipation should be perpendicular to this cross section, okay. So if you consider this R, okay, if you consider the sphere coordinate, okay, the vector that is perpendicular to this unit vector is nothing but R hat, no? Okay, so this S average should be in R hat direction, okay. This is average should be in R hat direction, okay. So we will consider like this, okay. Okay, so I think that is correct, okay. I will check it anyway, okay. So it should be R hat, okay. So if you consider this one, okay, this one will be the magnitude of this vector, okay, and you are getting the absolute value, no? Magnitude means you are getting the absolute value. That means if this is a real, that this it can be complex or real, okay, we don't know, okay. So if you get the complex value, you have to find the magnitude itself, okay. So if you consider the part, so this is the magnitude of the vector, okay? Still this can be a real or complex, okay? Still this can be real or complex, okay? So you know that this sine theta we can measure, jkr those we can measure, and neta jkl all can be measured, okay? Except this I, okay? So if this current is a complex one, this whole terms will be complex, no? Okay. So other parts will not contribute to be real or complex, only this current, okay? So you have to consider the magnitude of this current, okay? Also, okay? So this is the magnitude of the vector, and if you consider the magnitude of current, you will get the absolute value, okay? So its average will be, okay, its average will be magnitude of these terms. This is the magnitude of the vector, okay? So that is magnitude of jki l neta naught 45r sin theta to the power minus jkr minus jkr r, and you have to get the magnitude, okay? And this is in r hat, okay? So you have to consider the magnitude of this one, I, okay? So this part also complex, no? This also complex. This also complex, I'm sorry, okay? So this is also complex, okay? So what is the magnitude of this one, okay? So this is actually the complex part, okay? So we have to remove this complex part. The magnitude is here 1, okay? So if you get the magnitude of e to the power minus jkr, the magnitude will be 1, okay? So this part also will be cancelled, okay? So that will be 1, okay? That will be 1, okay? And this should be divided by half nu naught, okay? Nu naught, neta naught, okay? Half neta naught, okay? So you will get this one, okay? And so if you get the square, so it will be j square, okay? J square, and so I will write it here, okay? It will be, so the half neta naught is there, okay? And you, oh, sorry, this j also we have to remove, no? Because this is the complex also. This j is also complex, no? So we have to remove that one also. I'm sorry, okay? So you can see that, okay? I will tell it again, okay? So you want to get the magnitude of this E. You have to get the magnitude of this C. You have to get the magnitude, okay? So this is a vector, okay? So if you consider this vector, this is the magnitude part, okay? So you have to consider this one, okay? So when you have considered this one, this can be a complex or real, okay? And again, you have to get the absolute value here, okay? You have to get the absolute value here. To find the absolute value, you have to get the magnitude of this complex number, okay? So this part will be a complex, okay? So that is removed, no? So total is a complex actually, if it is divided by j, okay? So the magnitude is, if this is jx, x is square, and you have to get the square root, no? Again, you will get x, okay? So magnitude will be without this j, okay? And this also a complex part. Magnitude of this one is 1, okay? Okay, and this can also, this I also can be a complex, okay? So you have to find the magnitude, that one also, okay? But here we are not given the I, okay? So we have to get the magnitude of I, okay? So finally we have, this j is not here, okay? We have k square. So you have to consider the magnitude of I. You have to get the square, okay, and L square, theta square, sine theta square. This one, no? Yeah, these two, okay, and 4 square 16, 5 square, 5 square, R square. So this is in R hat direction, okay. So this is this average. Okay, so you can see that this theta and this one can cancel out, and this is 2 multiplied by 16. Okay, so you will get, okay, so I will take this one, I square. Now you have k square, L square, sine square theta, theta naught. Okay, only theta naught is there, divided by 32 5 square R square. Okay, so this is the average. So the the power radiated through a unit cross section from the R distance. Okay, so if you consider the antenna is here. Okay, so if you consider a R distance, okay, so it is a sphere. No, it is it is in 3-dimensional space. Okay, so it can be a sphere. Okay, so you can see that if you consider this antenna. Okay, so this is a infinitely small dipole like this. Okay, so what is the theta? Theta is, if you consider this is Z, okay, so theta is here. Okay, so theta is like this. Okay, and phi is this direction. Okay, so you can say that the average power is not depend on the phi. Okay, so that is constant along this one. Okay, so if you consider antenna like this, okay, okay, if you consider this is the antenna, if you consider this space, okay, so that is not changing, no, it is uniform. But if you consider this direction, theta direction, okay, so you can see that it is changing. Sine square theta is there, so it is changing due to theta. Okay, so it is changing with the theta direction, no? Okay, so I think you can understand it. Okay, so if you have the antenna like this, so you have placed the antenna. Okay, so the antenna is in now this way. Okay, so this is the Z direction, no, sorry, theta direction. This is the theta direction. Okay, and the perpendicular to this one is the so this is perpendicular to this one. Okay, so this is inside the paper. Okay, that plane. Okay, so this is inside the paper. Okay, so this is the phi direction. Okay, so the phi terms is not there. Okay, so it is same through the phi direction, the average power. Okay, it is not changing. Okay, but if you consider this direction, it is changing. No, it is changing like this with sine square theta. Okay, actually the theta is measured through this one in this direction. No, so the theta is 90. Theta is 90 means you will have the most power. Okay, you will have the most power. So the most radiation is happen in this direction. Okay, so you can see that radiation is not uniform along this theta direction. Okay, along this theta direction it is not uniform. Okay, so the maximum radiation you will get in this direction, and this direction and this direction you will get zero radiation, no, because sine 0 here, it is sine 0 and sine 180. sine 0 and sine 190 is 0, so there is no average power through this direction, okay? And only power is radiating in this direction, okay? So you can see that the radiation is not uniform, okay? And it has the most of power radiated through perpendicular to antenna in this direction, no? Okay. According to this diagram, if this is Z, the antenna is radiating in Y direction. The most power is radiating in Y direction. Okay. So that idea you can get using this parameter. So that is the average power density. Okay. So that is very important parameter. Okay. Okay. Now this is one another important parameter. Okay. So there is another parameter that is we called total radiated power. Total radiated power. Okay. So this is another parameter. Okay. So we have found the H field, the E field. Okay. So actually H field and E field we didn't consider as parameters. Okay. So these are not this parameter, this magnetic vector potential H and E are not in specification in the antenna, okay? But these can be considered as the antenna specification, okay? But these parameters are also not considered as a commercial specification, okay? We will see them later, okay? So anyway, you can calculate the total radiated power also, okay? And you can use this average power density, okay? So you know that, okay? You know that. Okay, I will explain it. Okay. So if you consider, again, we will consider the rectangular coordinate Z, Y, X. Okay. So this is a rectangular coordinate. Okay. And okay. So you are going to find this average in this point. Okay. So the antenna is radiating through this whole dimension. Okay. So it can be radiated in this way direction and also like this. Okay. So it is a sphere. Okay. So this will be theta and this will be phi direction. Okay. And this is the R. Okay. This is the R. Okay. So this is a sphere. Okay. So if you consider a very small area on this sphere, okay, let's mark it as ds. Okay, so this is a very small area across this sphere. Okay, so the average power across this density is nothing but SAVG. Okay, so this is the average power density through this small, sorry, the average power density is, sorry, so if we consider the average power density, okay, let's say that it is SAVG, okay, so this average power density is the power radiated through a uh, unit cross section. Okay, so total power, okay, so SAVG is unit. Okay, so unit cross sectional, you are radiating SAVG power. That is the definition, no? Okay, so if you want to find the total power, okay, total power through ds through this small area, it will be SAVG into ds. Okay, so this is the total power radiated through this ds, this area. Okay, now if you want to find the total power all over this sphere, what you have to do? You have to, if you find the total power radiated through this whole sphere, what you have to do? You have to evaluate this AVG with respect to ds all over this sphere. Sphere cross section, no? Okay, so you have to do a surface integral. Okay, surface integral of this sphere. Okay, along this sphere. Okay, if you evaluate the total the surface integral of S average through this sphere, you will get the total power radiated. Okay, I think you can understand it. Okay, so the total power radiated is nothing but, okay, you have to do the surface integral through this sphere. Okay, this AVG ds. Okay, so this is how we find the total radiated power. Okay, so we will see how to find this one. Okay, now okay, now and we know that this S average is a vector. Okay, and this ds also should be a vector. Okay, so the total radiated power is nothing but the total power. Okay, so this is the total power radiated or passing, radiated by the antenna, the total power radiated by the antenna. Okay, by the uh, antenna, and that the total power the passing through this, okay, through this sphere, total power radiated, so so it is, we can say like this. Okay, the total radiated power of the antenna, total radiated power of the antenna, okay, that is crossing or passing through this sphere, through the surface of this sphere is the total radiated power. No? That is the total radiated power. Okay, total radiated power. Okay, and you can see that this should be a vector, and also this is a vector. Okay, so you can write this radiated power, total radiated power, okay, as the surface integral of the magnitude of S average. Okay, so this is the absolute value of S average into ds. Okay, like this. Okay, so you can use this identity to calculate the total radiated power of antenna through the surface of the sphere. Okay, so that is uh, the round antenna, no, total dimension. It is a sphere, no? Okay, okay. Now, so how to calculate this one? Okay, so we have to evaluate this integral, no? This surface integral. Okay, so we will try to do that one. Okay, so if you consider, so I will write the um, rectangular coordinate like this. Okay, so you have to consider a sphere. Okay, so this is a sphere. Okay, you have to consider the sphere like this. Okay, so this is a sphere. Okay, so if you consider uh, consider a small cross section, we will try to write this. Okay, so it is the sphere like this. Okay, so it is a sphere like this. Okay, this is not a circle. Okay, it is a sphere actually. I'm sorry, I can't draw it very well. Okay, okay, this is X. Okay, so if you consider a small cross section, okay, like this. Okay, so these are curves. No, you can see that these are curves. If you, because this is sphere, no, so if you consider a small dimension, these are curves. This is a curve, and this also a curve. No, like this and like this. Those are curves. No, okay, okay. So how to find this length? Okay, so let's say that this is the ds. Okay, so how to find this length? Okay, so you have to, anyway, you have to, so this is sphere. Okay, so if we are using spherical coordinate, it is easy. Spherical coordinate, to evaluate this integral, it will be easy. Okay, so I am going to use the spherical coordinates to evaluate this integral. Okay, because it is easy. Okay, because we are doing the surface integral through this sphere. No? Okay, so you know that. So if you consider this one, okay, so this is, if you consider this as r, okay, this is as r, and this should be theta in spherical coordinate. So I'm finding a location, okay, small location, okay, and this will be 5. Okay, so this is r theta 5. This is the location. Okay, so if you consider this location r, okay, and if you want to find the length of this curve, let's say that is the length of this curve is dl. Let's say that it is dl1, and the length of this curve is dl2. What is the dl1 and dl2? Okay, so if you consider dl1, okay, so it is like this. You have a circle like this, okay, and you have a r like this. Okay, okay, and if you consider uh, very small theta, d theta, let's say that is small angle d theta. Okay, yeah, so this is a circle. Now this is not sphere. Okay, I'm considering this 2D plane also, this YZ plane. I'm considering this YZ plane. Okay, so it is a circle. This is not a sphere. This is a sphere. ZYX. Okay, so this is a sphere. Now I am considering the portion along this Z and Y plane. Okay, so it is a circle. No, Okay, so if you consider very small theta, let's say that d theta, okay, because this is in xy plane, no, theta is in zy plane, sorry, theta is zy plane. So you have, if you have considered very small uh, angle, so this is the radius of the sphere, okay, then what is the value, what is the length of this part, okay, so we have put it as dl1. What is the length? That is r d theta, no, okay, so this is the, so this theta is the radians actually, okay, so this is the definition for radians, no, this is the definition of radians, okay, so this so you know that this length, okay, if you divided this length from the radius, you will get this angle d theta in radians, okay, so let's assume that these are measuring in radians, okay, so these are measuring in radians, so this is dl1 is nothing but r d theta, okay, so that is dl1. And what is dl2? Okay, so that is dl2 means you have to consider the xy plane, okay, so if you consider the xy plane, okay, so that circle is like this, okay, so it is in xy plane, okay, so it is in xy plane, this is x and this is y, xy plane, okay, so you can see that now you are uh, considering uh, this point and this point, no, you have to consider this point and this point, okay, so what is that point, okay, so that is, this is r and this is theta, so it will be r sine theta, okay, so so if you consider this is pair, okay, if you consider this is pair, okay, like this, okay, now you are going to find this, I will write it here, okay, now you are going to find this dl2, okay, this dl2, this curve length, okay, so it is in xy plane, okay, so it is in xy plane, okay, so you can see that, so this is r, no, okay, so you have to go inside the paper, no, inside the paper, xy plane, okay, so what is the length, okay, so what is the length, so xy plane, you have to get the projection for the xy plane, no, so that is r sine theta, okay, so that is r sine theta, okay, so that is the xy plane r sine theta, and you have to move, okay, let's say that you are moving d5 angle like this, okay, so this is dl2, okay, and you are getting d5 angle, okay, so this is in xy plane, so you have to get the projection, okay, so this is r sine theta, and also this will be the r sine theta, okay, so what is this dl2 is nothing but r sine theta d5, so this is the dl2, okay, so ds means dl1 this length and this length into dl2, okay, so that is dl1 is r d theta, dl2 is r sine theta, so you will get r square sine theta d theta d5, okay, so instead of ds you can put this value, okay, so dt is equal to, you have to do the integration is, okay, savg absolute value r square sine theta d theta d phi. Okay, so you have to consider, you have to do the evaluation in d theta and d phi, so it is a double integral. Okay, so you have to evaluate it through this, and you have to evaluate it through this. Okay, so you can see that if you are evaluated it in 5 direction, it is this, no? This is the total direction you have to get for the 5 direction. Okay, so you have to get this total direction 5. Okay, so dt is equal to 0 to 25, no? 0 to 25, this is in 5 direction, and also you have to evaluate it through the theta direction also. Okay, for the theta direction you have to evaluate it from here to here, no? Theta direction you are evaluating it from here to here, and phi direction you are evaluating it from here to here, the whole surface. So you will get this one and this one, but as well as, okay, so you can get the full sphere, no? Okay, so at the, for the theta you have to evaluate this from 0 to 5. That's enough. Okay, then you will get SAVG r square sine theta d theta d phi. Okay, so you can calculate the total radiated power like this using the surface integral. Okay, so for a dipole, infinite small dipole, we know that Pt is equal to 0 to 25, 0 to 5. So this is SAVG, the magnitude of SAVG. So what is that? Okay, the magnitude is, so this is the SVG, no? Okay, so the magnitude is this part, no? This part, this is the magnitude. Okay, so it is a real, no? So you have get the magnitude of I also. So this will be the real part. Okay, so this is the magnitude of this AVG. Okay, so if I write it, okay, I can write it as, okay, so this should be I square, K square, L square, N square, K square, sine square, 32 pi square, R naught T, R square, sine theta, d theta, d phi. Okay, so it will be theta, okay, K square, pi magnitude square, L square, sine square theta, divided by 32 5 square r square. So this is the magnitude of SAVG. Okay, the average power density magnitude. Okay, and it should be multiplied by r square sine theta d theta d phi. Okay, so what is the value we get here? Okay, so you can see that r square cancel out, sine square sine theta, so sine theta to the power 3, sine to the power 3 theta. Okay, so you will have like this. Okay, so you will have like this. T is equal to 0 to 5, 0 to 5. Okay, not K square, I square, L square. Okay, and here 32 5 square, 32.5 square sine theta d theta d5. Okay. So this is the, so this integral you have to do this sum. Okay. So you can see that this integral is very easy because there is no 5 terms here. But when you are going to find it d theta, you have to evaluate the sine square theta, sine to the power 3 theta d theta from 0 to 5. Okay, so you have to do this integral. Okay, either you can do it using trigonometric identity. Okay, trigonometric identity. Okay, so try to do it by yourself. I think you have done this kind of integral. Okay, so these are standard integral actually. So you can calculate them by yourself. Okay, so once you integral it, this with respect to d5 from 0 to 2, 5, you will get the value. Okay, so if you evaluate this integral 0 to 2, 5 d5, okay, you will get 2, 5. Okay, so that is very easy. Okay, so okay, so you can get okay, so try to do this evaluation by yourself. Okay, and your value will be, okay, so I will write the final value here. You will get theta naught a square I magnitude d square L square divided by 12.5. Okay, so you can see that this is divided by 2, 5. Okay, then 5 and this 5 cancel out. Okay, this 5 cancel out. Actually, this value you will get 8/4. I think 8/3. I think, okay, as I can remember, this is 8/3. Okay, so you can evaluate this. Okay, try to do this one. Then you will get this answer finally for the total power due to infinite small antenna. Infinite small antenna. Okay. Okay. So this is also very important parameters. Okay. Then again we have to find some parameters related with the antenna. Okay, and we will see them in next time. Okay, in the next lecture I will tell you how to calculate. So we have to study about some new parameters. Okay, so in the next lectures we will see how to calculate those new parameters. Okay, so I will stop here.